is not. It is not a metronome or a clock. While there are numbers around the circle and they do represent hours, unless your planet has a 42-hour day, you will be hard-pressed to actually track time with this. And it is also not a perpetual motion machine. We're not asking you to be amazed how it goes back and forth indefinitely. And you come back later and it's still going back and forth. No, the fact that it goes back and forth indefinitely is because there's an electromagnet all the way up in the rotunda, which pushes it back the way it came, or more precisely, it pulls it back the way it came every time it reaches its apex. So you can actually see the string wobble a little bit every time it goes from one side to the other. And that is the electromagnet pulling it back the way it came. So basically all it does is make sure the pendulum goes in a straight line. And so the purpose of going in a straight line is allowing us to ask a fairly simple question. Does the pendulum knock over the pegs because the pendulum is wobbling and knocking them over because it's going in a strange direction, or are the pegs moving in front of the pendulum? And with the pegs are sitting on a tray, so the answer kind of counterintuitively is actually the pegs are sitting on a tray and they are getting in front of the pendulum. And they are doing that because the Earth is rotating, because the pegs are sitting on a tray, and the tray is sitting on the ground, and the ground is sitting on the Earth, and the Earth is doing what planets do, and is rotating. Now, that seems strange because most things about the Earth's rotation we don't notice. Because you see the horizon, but the horizon does not go up and hit you in the face because you are moving with the horizon, you're moving along with the whole planet. But the purpose of a pendulum experiment like this, called a Foucault pendulum, it was invented in 1861 by a French physicist named Jean Foucault, a Foucault pendulum. The purpose of this device, all it is a proof that we are on a rotating planet. And in that sense, it's a very straightforward science experiment. But it is actually, there are two reasons you use a pendulum like this. One is that, yes, the string of course is connected to the ceiling, and that rotates as well because the Earth is rotating. But the heavier you make your pendulum, the more you can mitigate the twist effect of the Earth's rotation on the string. So this pendulum weighs about 240 pounds. It's very heavy. It's brass. It's very solid. And so that minimizes the twist effect. And the other part of using a pendulum like this is easier to show than to explain. So here's my little small pendulum, and it's going more or less back and forth. Of course, I have wobbly human hands, so this wobbles a little bit, but the idea here is it goes back and forth in a straight line. And even though it's on a rotating base, notice how this globe is rotating. So this is going back and forth, and I could really make it a little straighter, so it goes back and forth. Now, if I'm hanging out here in, let's see, it's Soviet Russia because our map is really old. I'm hanging out here. I'm not moving by the way we consider it. I'm still in the same place, but the Earth is rotating. So I have run into the pendulum because I have stayed in the same place, but I have moved along with the planet and run into the pendulum. In much the same way, these pegs stay in the same place as we think of it, but they are moving along with the Earth, and they move in front of the pendulum, and it is the pendulum that is effectively cut off from the Earth's rotation, and it is going in a straight line relative to when it was started, not a straight line relative to the Earth's spin. So this actual whole experiment, if you do it properly, you have a full circle of pegs all around the circle. But now we kind of like dealing with dominoes, so we don't do that. We just have to try and move it. But if you do this experiment different places in the world, it actually takes more or less time. So if you do this experiment at the North Pole, it actually takes 24 hours to knock down a full circle of pegs. But so that if it was here on the North Pole, as seen in our models, it would be here. Now here in Los Angeles, however, we're at 34 degrees latitude, and we actually it only takes it takes longer. It takes 42 hours to knock down a full circle of pegs, and it takes 7 or 8 minutes per peg, and that's what you see every 7 or 8 minutes. So that's why our numbers around the circle from 0 to 42, because it takes 0 to 41, which makes 42, and that is the amount of time it takes to knock over full circle of pegs in Los Angeles. Now, if we were to do this experiment at the equator, it would actually not work at all. You take the whole thing down here, and gravity pulls it in, but actually you knock over the first peg and the last peg, but the experiment wouldn't actually work, because you would be going along with the Earth's equatorial motion, and you would not be able to notice any change in the peg's movement, because the pendulum would be going exactly along with the Earth's rotation. Now, that's sort of a theoretical location, the exact equator, but the closer you get to the equator, the longer this experiment will take. So, we put this in our lobby as the first thing people will run into because it is a very physical and tactile way of showing you are on a planet. It is true what planets do, it is spinning. There are ways to prove that, and we have many other exhibits here at the observatory. Please enjoy them. And follow the sky, various exhibits on the moon and the sun and the Earth. And there in the Hall of the Eye, we have various exhibits on telescopes and the EM spectrum. And we do have 2 lower levels that were added in the renovation. You can reach them by the elevator or the staircase behind this wall. So, if you have any questions, please don't hesitate to ask the various museum guys, see if you about the building, with little badges, and have a good evening. That's not the end of the world.